4.4 will be the last of the videos I force you guys to watch this weekend, partially because I'm up in Big Bear in a cabin, locked in a bedroom by myself, making a video for you on Friday night, and also partially because I feel like we've had a lot to digest. I'll probably post up 4.5, our final video, between Tuesday and Thursday, and then we'll cover the sampling questions on Thursday. 4.4 is a big, meaty section. It'll probably take 2 videos to get through. This section is going to cover probability displays. We have a lot of ways to display probabilities. We're going to cover 3, 2 of which are going to, well, I guess we're covering 4, 3 of which are going to be very important, and 1 which will become important as we move into part 5. The first one, which is not as important now, but is the simplest and will become important, is a discrete probability distribution. So when we're dealing with mutually exclusive or disjoint events, we can actually list out every single event and the probabilities of those events occurring. So that's what a discrete probability distribution allows us to do. In this particular example, we're using the word discrete because we're looking at the number of red lights a commuter is going to hit on her way to work. And the outcome here, this number of red lights, our random variable, so to speak, has to follow a discrete quantitative variable. You cannot hit 1.5 lights on the way to work. It's only 0, 1, 2, or nice countable numbers. So remember, discrete versus continuous, we're dealing with something discrete here. So it looks like there are 5 lights total on her way to work. She can have a really good day where she gets there without hitting any lights, or a really bad day where she hits all 5. All right, so before we even get into the actual questions here, we're missing one of our days in this little thing. We are missing the probability that she hits 3, one of our options, the probability that she hits 3 lights on the way to work. So how are we going to find that? Well, if this is every possible outcome, that means our entire sample space, we know the probability of that entire sample space must be 1 or 100%. So these values that we have down at the bottom must sum to 1. So we could add all the existing values up, and then we could take that value and subtract from 1 to figure out what we are missing. Turns out if you do all that math, we are missing 15%. So the probability of hitting 3 lights on the way to work for this commuter is 15%. Our first question here asks, if we're selecting one trip at random, are the events above disjoint? And as I said, these discrete probability distributions are used for disjoint or mutually exclusive events because there is no way on one trip she can't hit 1 and 2 lights. All right, we could easily have had this set up in a different format where maybe we're looking at hitting the first light and hitting the second light on the trip, but this is the total number of lights she has hit, and at the end of the day, it's either 1 or it's 2. There's no way she can be both. So at this point, I want you guys to try pausing the video and take a stab at the 2 left examples. Okay, so we have 2 examples here. One that says, what is the probability that she hits at least 3 lights? So like I said, this critical reading is very important when we get into part 5 and we start looking at the binomial distribution. For now, it's sort of this own separate little piece. So hitting at least 3, well, that's hitting 3 or more, right? At least 3 is 3 at the very least. So our outcomes 3, 4, or 5 lights are the ones that we care about. And since these are nice discrete events, you could write probability of 3 or 4 or 5 and use the addition rule, or you can just more common sense this particular question in my mind and just add those probabilities all together. But the reason we're adding them together is essentially that we're using the addition rule for disjoint events. And then the next question, probability that she doesn't hit all the lights. Well, hitting all the lights would be 5, right? And we're interested in not hitting all the lights. So any of the other ones. and you have your options, just like the iPhone question from 4.2, we could sit there and add up all those other outcomes, just like we did in the last question in part B, or we could do 1 minus hitting all of them. Oh God, I did not mean to box that up. I meant to actually write equals 0.95. So there's a 95% chance that she won't hit all of the lights on her way to work. She won't have the world's worst commute on that particular day. So again, we won't probably see much of this. It will be the thing that we use again and again when we get to part 5. For now, we're getting to the big 3. So 2 of the big 3 are our contingency table and our Venn diagram, and we've already seen both of these. Now we're just going to formally write them and insert probabilities into them, because when we saw a contingency table before, when we looked at very happy and male, right, we had the counts, the number of people, but we could have made this a relative frequency table as well, where we had the proportions or the probabilities in there instead. So no matter what, in our contingency tables, we're only going to look at 2 events here. We have 2 events. We have A and we have B. And when we're doing contingency tables or Venn diagrams, we want to have those 2 events be able to intersect. So we need to have A and B on opposite columns and rows. So that way, where they intersect, that's the probability of A and B. So you may ask yourself, well, what goes next to A then? Well, if they're not in A, they are not in A, right? We'll use A complement. Same thing here. If they're not in B, they're B complement. And then we do have one final section here that I've made in my little contingency table, right? Life is a lot easier when you have your total columns and total rows. So you don't have to sit there and add everything up on the fly when you're doing problems. So we can now fill in this entire sort of table. All of the middle pieces are ands, and it's just about what 2 things intersect. So here we have the probability of A complement and B complement, because A complement and B complement are what the intersection of this cell is. We have A and B complement, and then we have the probability of what we call neither nor, not A and not B. And then if you go to the total column, this is where you're going to find those marginal probabilities. Here, we've taken all the people in B who were also in A, all the people in B who were also not in A, and we're adding them together, we get everybody in B. And here we're going to get the entirety of B complement. And then we have our A's and all of our A complements. If you add B and B complement together, you get everyone. And when we're talking about everyone in a probability sense, that's 100% or 1. So that's our contingency table without numbers, but just thinking about the symbols and where they fall. So our contingency table gives us all of the ands and all of the marginals. The only thing it's missing are ors and our conditionals, but we can get those by using our formulas. So this also brings us into the Venn diagram. So the Venn diagram does the same thing. It displays our joint probabilities just like the contingency table does. And again, just like the contingency table, first thing we need to do is set up A and B. We have our A and our B. Sorry, I paused, so that was probably weird. I was talking and then I stopped talking and now I'm talking again. Our A and B must intersect. So we're going to call one of these circles A and the other one B. That way, that middle section is the intersection of our A and B. We can put our probability of A and B right there in the middle. The rest of it gets a little trickier. We have 3 more spaces in the Venn diagram. There's this space, and the space that includes neither of the circles. The most common mistake when it comes to this Venn diagram is to just say that this thing is a probability of A, which it is not. The probability of A is the entire circle. Remember, we saw this before. This whole thing is a probability of A. When we're talking about that little empty spot there, this is being in A, but not being in B, right? So it's A and B complement. Whereas over here, we're in the B circle, but we are not in the A circle. And here, we're in neither of the circles. So the Venn diagram takes these middle 4 probabilities and displays them, right? All of our joint probabilities. It doesn't have those totals in there, so it does lack a little bit in terms of using it to find probabilities and such. It's a little bit harder to work with, and students make a lot of errors with it. So let's go ahead and see these in action in the next question. So our first exercise here has us looking, second, I guess, because that discrete one, but our first real exercise is definitely kind of test question worthy. So I want you, first thing, practice that notation again. So I've even told you in this particular question, computer science major is A, discrete math is B, which means I'm being mean and making you use letters that don't really make sense, but we can do it. So I want you to go through, remember what we did before, look for all the probabilities, and then the thing we're looking for, translate all four. So I'll set up the beginning of this. You have a 13%, you have a 15%, you have an 84%, and you have the probability that you're looking for. So I want you to pause the video, see if you can get this notation right. All right, so what you should have done is read through and kind of look at each probability. So the 13%, only thing in that particular sentence is computer science major. Nothing about discrete math at all. So this is our A by itself. The next section, 15%, nothing about computer science, just says that they're have taken discrete math. B by itself. Our 84% are not computer science majors. So computer science was A, but we have not A, right? So this thing is A complement. And, we love that keyword, have not taken discrete math. Again, make sure you read carefully. So this is our B complement. So we have A complement and B complement. I used my and notation from math because I didn't have enough space to write the word and. Now the last question here. What is the probability that a student is a computer science major, nothing about not being computer science major, so that's our A, but has not taken a course in discrete math? So we have our B complement. And then we look for our keyword. We look for our and, we look for our or, our of, our if, or our given, and none of them are around. The only keyword we have in this particular question is the word but. And I want you to take a moment and decide, does it make more sense for but to be an or a given? And but is just a conjunction, right, in terms of grammar. And that means but is basically another way to say and. It's just an and that is followed by something was the opposite of what we might expect. So we are looking for this and when we have this one. Now this is something on our formulas. All we have for formulas are ways to get to and if we have a conditional or an or. Not when we have another and a bunch of weird stuff, right? Nothing here is going to help us. I can tell you a desperation move would be to figure out B complement and maybe multiply them together like they're independent. But we haven't proven that. So this is where the contingency table would help. If we use our contingency table, we can use the fact that we know that all the rows and columns sum. That was what we did in the class example with major versus gender, right? We could add up all the different females of all the different majors and we knew how many total females were in the course. So we can do the same thing even if we're dealing with probabilities instead of numbers. So we're going to go ahead. Probability of A. I want you to take a second, figure out where you think A would go in the contingency table. Now, if you remember what we did in the last example, when we just wrote out all the crazy probabilities, A does not go here because this is A and B. That would be the most common mistake. A has to go all the way down in the A total column. And B is going all the way in this row total of for B. And then A complement and B complement will go here. Now, this is all we need. 3 pieces and we can fill in the entire table as long as we have the 2 marginals and a joint. The way we do that is that we know one more piece of this table. We know everything sums to 100% or to 1. So if 15% of people have taken discrete math, that means 85% of people have not. And if 13% of the students are computer science majors, that means, well, 87% are not. And that even works down our rows, right? We can see if I add these 2 things together, they should equal 87, which means this particular cell must be 0.03. And it works in the rows as well. This plus this equals 0.15. So we must be missing a 0.12. And all the way around. And the nice thing is that whatever you use to get this 0.01, you can check in the other direction to make sure it's right. So everything should sum down the rows and down the columns to get your final contingency table with all the probabilities. So now if we go back to our original question, the probability of A and B complement, now we're just, well, ands are what the table gives us. I just need to come to the table and say, okay, A, B complement, they intersect here. My answer is just 0.01. Easy, right? Happy. So now we're going to go through. I'm going to take a moment, have you guys pause the video. I want you to go through each of these questions, and for each of them, I want you to decide what probability are we looking for, and then see if you can figure out how you would find it using the table. Because this table is very similar to the one we conquered in class on Thursday, but a little different because we have probabilities in it. All right, so you better be pausing, because otherwise I promise you this is going to suck on Tuesday when you get that worksheet. So first question, take in discrete math, not a computer science major. So discrete math was B, computer science major was A, but we have that keyword of not, so we need to make that an A complement. And we have that keyword of but again, which is just a fancy ass way to say and. So here we're looking for B and A complement, which is another one to grab straight off the table. So B and A complement, right off the table, 0.03. All right, we keep moving on. Next one says, has taken discrete math, computer science major. No knots in there. I just always double check for the knots because that's a very common mistake on the test. So we have our B, we have our A. There's no and between it, no but between it, no or between it, which means this has got to be one of our conditional probabilities. And even worse, there are no ofs, ifs, or givens. So I've really made this one particularly challenging for students. On the test, I have never put one of these on there, but I could, right? You need to decide what is the piece that we know. And this part is the clutch piece that tells us this. Who has taken discrete math? This is the piece that we know. We know that they're a discrete math major. What's the probability that they're a computer science major? And now this is one that you need to use your formula to kind of set up. You could do it kind of intuitively from the table, and I'll talk about that in a second. But if you use your probability formulas, your conditionals are the and divided by the thing that we knew, the thing that was behind the line. So here we need the probability of A and B, which is 0.12, over the probability of all the B's, which is 0.15. Now, how would you do this intuitively? So again, you kind of do this like we did in the contingency tables with the numbers. Probability that someone who has taken discrete math. We're saying that we only care about these B people. Now, what is the probability that they are also a computer science major? Well, that's the part of our whole, right? So that's the other way to do this without using the actual formulas, is to think of part versus whole based on what piece we know. But again, you'll have the formulas on the test. It's just about knowing how to use them. All right, our last question here. Probability somebody, well, second to last question. The probability somebody's taken discrete math, so again, our B, or is a computer science major, our A. So we're looking for B or A. Another one where we need to use the formulas, because again, our table only gives us ands. So the formula for or, remember, add the two together and subtract off the intersection. So if we add the two together, B by itself is 0.15, A by itself is 0.13, and the intersection was 0.12. So there's a 16% chance that someone has taken discrete math or is a computer science major. So our last question here is the first time we've seen this, though we did talk about it in 4.3. Are taking discrete math and being a computer science major independent events justify your response? So we want to test if they're independent. If you go back to 4.3, we had two ways to test. One way is the way I sort of recommend for students. Use the independent rule that should be written down on your little note card. If two events are independent, there's our sweet multiplication rule. We get to use it. Super simple, super awesome. what we can do is plug in to see if this is true. If it's true, yes, they're independent. If it's false, no, they are not. So our A and B, we've used this number twice now, 0.12. A by itself, 0.13. B by itself, 0.15. Now all I need to do is multiply 0.13 and 0.15 and see if that equals 0.1. So we get, is 0.15 equal to 0.0195? These are not even close. And remember, we are now in math land. So if something is not exactly the same, we can say that they are not independent. If you think about statistics land, if this were 0.12 and 0.11, right, 12% and 11%, statistically, those are probably not different enough, right? But mathematically, 0.12 and 0.11 are not the same thing, and this is a pure math section. So those of you pure math people, remember, there are right and wrong answers, and everything is very cut and dry in this particular section. So since this does not equal, no, they are not independent. Now for me, this is always my recommendation for students because it's easy. It falls in line with that memorized or thing that we have in our note cards, the independent rule. But I like the other thing that we saw, that understanding of what independent means. So remember, we have this probability already, this conditional. If two events are independent, that means knowing one tells us nothing more about the other. So the fact that we know B is useless. It's not giving us any new information. So we might as well just have this equal the probability of A. And we can just try this out. We already calculated the probability of A over B. Not that I actually typed it into my calculator because I didn't have it. And this was 0.8. So probability someone who has already taken discrete math, is a math major, is 80%. Taking discrete math tells us a lot about whether or not they're a math major, right? Whereas the actual computer science major, I know what we're talking about. Whereas the probability of being a computer science major, it's only 13%. These are not the same. So no, they are not independent. But this gives me more information because now I can actually say what that relationship looks like. Not that there's just a relationship. I know the relationship. I can say someone who has taken discrete math, oops, forgot the take in. Someone who has taken discrete math is much more likely to be a CS major, right? If 13% of the students are CS majors and 80% of those who have taken discrete math are CS majors, I now see this relationship. I now know the direction of it and how it works. So that's why I like the second method personally, but either method is good on the exam when I ask you to prove something's independent or show something's independent using probabilities. This is what I'm going for.